And the situation that I want to study is illustrated here. So I want to consider two-dimensional waves past the body of a ship. Actually, in the last lecture, the picture that I drew was waves over a step, and then I realized that waves past a ship is a bit easier to set up in terms of the set of equations. But actually, we're going to see that the setup between either flow past a surface-piercing body like this, or flow past a submerged body, it's going to lead to roughly the same kind of equations and certainly the same theory. Okay? So, as we explained last time, we want to solve the Laplace equation for some kind of potential here, and we're interested in the prediction of the downstream waves, assuming that the flow is going from left to right. Okay? We set up our coordinate system so that y is equal to 0 is at this stagnation point. So we're going to make the assumption, it's not meant to be obvious, but we're going to make the assumption that as the flow goes past the rear edge or the stern of the ship, it's going to separate at a stagnation point here, which is going to be largely what's going to happen if it's slow speed or low speed or low fluid waves. Okay? And then the better way to visualize this system, not in the xy plane, is instead in the potential plane. So in the potential plane, you have the coordinate phi, the velocity potential, and psi, the stream function, and then a, b, c, d would be a, b, c, d. Okay, the free surface is mapped to the edge CD here, and then the solid body has been mapped to the edge here. And this relies upon the fact that in the situation of potential flow, the solid and free surfaces form a streamline with psi is equal to 0. Downstream, or infinite depth, would correspond to psi going to minus infinity. And then phi is effectively the coordinate that is 0 at the stagnation point. Phi is equal to 0 here. You also need to introduce a coordinate for the corner point here. So we're going to assume that the shape or the body of our ship is going to be in this rectangular form with an angle of pi by 2. But then actually we can do all sorts of different angles in a minute. So I'm going to assume that at this location, I know what the potential is, and it takes a certain value. So the notation is a bit confusing, but I can select what the value of the potential, velocity potential is at this point, and by normalization, you can actually select it to be minus 1. So this will just be set to be minus 1, and I don't need to introduce this a. Okay? So, as we also explained last time, you want to start to think of phi and psi together. And you can do this because of the fact that phi satisfies Laplace equations, and so psi, the stream function, is the harmonic conjugate of a new complex variable, which you call w. So, in potential flow theory, this w is the complex potential. Okay. And then also, as I explained, it's easier to think of w as a function of z. To reverse the independent and dependent variables, usually in this problem you think of phi as the unknown, phi as a function of x, y, but then it's easier to think of phi as a function of x and y. So x and y are the independent variables, and phi is the dependent variables. And it's useful for us to think of z as a function of phi and psi instead. And the value of thinking it in this way is that in this coordinate system, the free surface has been mapped to psi is equal to 0. So it's a known thing. So if I can write down a set of differential equations in this coordinate system, it's a lot easier to solve. Once I've solved the problem in that coordinate system, there's a way for me to integrate out and get the physical coordinate variables. Okay? Okay, so that's the basic idea. Now, as it turns out, there's an even more convenient variable to work with. Okay, instead of x's and y's, and the variable to work with is the speed and the angle of a streamline on the free surface. Okay, so you can, if you think of a particle that lies on the free surface, this particle has some velocity vector, and it has some speed, q, and some angle theta that the particle is oriented with respect to the x-axis. Okay? So essentially, your velocity vector, or your complex velocity, is u minus iv, the horizontal and vertical velocities. And in writing the notation in this way, what we've done is we've written it as q e to the minus I theta. Q is the speed of the particle, and theta is the angle that the particle makes with the x-axis. And it turns out that you can verify this, but this is essentially dw dz. It's the derivative of this complex potential with respect to x and y's, this complex derivative. So z is equal to x plus iy. And this follows, again, because of Cauchy-Riemann and various complex variable theory. Okay, so we're almost there. So what I'm saying is that it's going to be easier for us to work with q e to the minus I theta as the main unknowns to derive on the free surface, the speed and the angle of the particle. And even more confusing, it's actually easier to work with the logarithm of this thing. So if I take the log of that thing, I have log of q minus I theta, and I'm going to define that to be my variable omega. Okay? So omega is a function of phi and psi. Okay? And why this turns out to be easier is not meant to be obvious at all. It's just easier to think of. It's easier once you write down your sets of equations. It took people a long time to get to here because they were working with all sorts of different formulations of the water wave equations in 2D. But after about a century of work, people realized it's best to write it in this way. Okay, at least for this problem here. And so it's going to be particularly elegant to write it in terms of log q and I theta, log q and theta, which are the real and complex parts of this new big unknown omega. So remember now that you're trying to solve for this big omega in this domain as a function of phi and psi, and in particular, you want to know the values of omega on phi greater than 0 on this free surface from C to D, because in doing so, you'll derive the velocities q and theta of the wave along the free surface. And there's a way, once you've derived q and theta, there's a way to use this relationship basically by integration to get back the x's and y's. So once you get q and theta, you can get the physical location of the free surface. Okay? Okay, so this is the basic idea. Now, there's kind of two components to writing down your set of equations. You're going to need two sets of equations for the two unknowns. The two unknowns will be the log q component and the theta component. One set of equations is going to be given by Bernoulli's equation. Okay, so Bernoulli's equation tells you that you have this balance of inertial and gravitational effects on the free surface. So it's a condition that you impose along the free surface, and it basically tells you that epsilon over 2 times the speed squared plus y is equal to 0. So we've non-dimensionalized Bernoulli's equation. Epsilon is the Froude number, or the square of the Froude number. So remember, epsilon is the square of the Froude number, which is u squared over g times L. Okay, so u is the speed of the flow at infinity, g is gravity, and L is a length scale which is actually going to be related to the fact that we were able to normalize this potential at -1, but it's not so important. It's basically a length scale that characterizes your ship. Okay, so gravity this is like 1 over gravity, And this is the speed squared, so this thing here is q squared. Okay? So we'd like to write now this equation in terms of q's and thetas, and the way to do that is just to take a derivative with respect to phi. So remember, phi is the velocity potential, the velocity potential. And if I take a derivative of this equation with respect to phi, I have something like epsilon times q times dq d phi plus dy d phi. But then I can use the relationship of z's and phi's that we had written out earlier to show that dy d phi is actually just 1 over q times sine of theta. So now I can multiply by q, and I'll have epsilon q squared times dq d phi plus sine of theta is equal to 0. So you can see how this is starting to become a bit more of an elegant formulation. We now have a differential equation involving q as a function of phi, and sine and theta as a function of phi. And remember, phi will primarily range along the free surface from 0 to infinity for phi. We've got one set of equations. We need a second set of equations to close everything. And the set of equations that we haven't used so far is the fact that this is the potential fluid. And so you should satisfy Laplace's equation. So when you deal with potential flow theory, the way that you can impose Laplace's equation is that Laplace's equation is often shown to be equivalent to an integral along the boundaries of your problem. Okay? So in this case, we look at the variable omega. Right? Omega is a function of phi and psi, or you think of omega as a function of the complex variable phi plus I psi, and this is w. So you have a complex function, omega, as a function of w. W is, remember, w is phi plus I psi. Okay? So this is basically log q minus I theta. And remember that log q just tends to 1 at infinity in your flow. The speed tends to 1. And so you can verify that this is an analytic function, and so you can oppose Cauchy's theorem. So Cauchy's theorem tells you that whenever you have a complex analytic function like this, you can write it as an integral 2 pi I over a contour of the function itself over this denominator. Okay? And the contour that you're going to choose is basically just going to run, I'll draw it down here, in the potential plane, or the w plane. So this is the w plane. It just runs along the solid surface, then the free surface, and then it does a little deformation down there. And so w is a point here. Okay, so this is your Cauchy's theorem that tells you that the value of omega at some point w within this boundary is somehow equal to an integral of omega around the edges of the boundary. Okay? So now what you can do is you can basically take this point w and approach it towards the desired location that you want to evaluate your function on. And you want to know what the value of omega is on the free surface, and the free surface has been mapped to this edge, CD. And in doing so, right, you're going to find that this integral is going to split into a value which is basically an integral from minus infinity to a point, and then a little contour around the point w and continued on to positive infinity. Okay? And so this integral will split into this this integral that goes from minus infinity to a point and that point to infinity, plus a residue contribution. And then when you move the residue contribution to the other side, you can then take the real part and the imaginary part of the resultant set of equations. I'll write down the final set of equations that you're going to get, but that's the basic idea. It's not the fine details are not so important for us. But we do that process where we write it in terms of a boundary integral, and then you basically take the real part of that, and you're going to end up with log q is equal to 1 over pi. I'm going to explain that integral with a dash through it in a second. From minus infinity to positive infinity of theta okay? So this is what you're going to be left with when you take the real part of that process that I explained to you before. Remember the real part of the left-hand side, that's why you had the log q. And then the real part of this right-hand side, there was an I in front, and that's why you end up with the theta. Okay? This integral with a dash in front of it just means the principal value integral. Okay? So what this integral means is that, remember, phi is evaluated somewhere along this axis from C to D. That's the free surface. And so this integral will be, the integrand will be singular at this point here, at the desired point phi. So you end up splitting it. You split the integral. So this integral is basically the integral from minus infinity to 0, firstly, because this is non-singular. Phi is valid on the right here. Then you have to add a bit from 0 to phi minus something small, and then from phi plus something small to infinity, and then this is theta. Okay, so these two bits together is what the principal value is defined as. It just basically means that don't integrate right through the singularity, integrate right to a little bit left of singularity, then a little bit right all the way to infinity. This integral here, the integral from minus infinity to 0, is non-singular, right? Because remember, phi is valid on the free surface, and so this denominator will never hit 0 for the integration along the left edge here. Okay, so what you can do is you can split this integral up into the values from minus infinity to 0, and then from 0 to infinity, as we've done here. And then you know something about the angles of your ship on the left. You know what the theta values are on this edge. You know that theta is 0 from A to B because it's flat, and you know that theta is pi by 2 from B to C. So you can simply put those into the integral and see what you're left with. Okay? So if you do that, you're going to be left with, and you just integrate, it becomes a logarithm. It's not too hard to integrate. You're going to be left with the following. Log q is equal to the integral of log. Remember here that, let me just write the independent variable because you might be a bit confused. You want to know what log q of phi is. It's the integral of, it's the logarithm of phi over phi plus 1 to the 1/2. This 1/2 came from the fact that you had a 1 over pi, and then you put in the angle along that edge of pi by 2, and then you just integrated it. All right, and then this was 1 over pi, principal value from 0 to infinity of theta. Okay, remember that phi is, this phi, there's kind of two phi's that happen in this equation. There's the dummy variable phi, which is just the integration variable, and then this is the thing that you're trying to evaluate. So for every value of phi that you want to know q at, you put that into here, you try to integrate from 0 to infinity. Okay? So you have one set of equations. You see this set of equations, which relates q and theta together, and then you have one set of equations, which is epsilon q squared q prime plus sine of phi, so sine of theta is equal to 0, and you're going to try to solve this Okay, you need one boundary condition because this is a first order problem, and so you're going to try to solve this with q of 0 being 0 because the speed at the detachment point should be 0. And you're trying to solve this for phi greater than 0. Okay, so we've now compressed, in some 20 minutes, we've compressed all your 2D potential flow equations into this very elegant system of two equations for two unknowns, the q and the theta. The unknown the independent variable is the phi that runs from 0 to infinity. Q should start from 0 at the stagnation point. And it has, what makes it complicated is not just a simple differential equation here, but it also has an integral equation. But this integral equation, you can think of it as essentially you can substitute the value of q into here, and then now you have an integral differential equation, if you like. It's an integral differential equation for the theta, right? But it's still a bit complicated. It's not as simple as differential equations that we looked at. Of course, it's still a nonlinear differential equation. It's still complicated, and it's got this weird component here with the integral bit. Okay, let me show you a script in MATLAB where we can solve this equation in something like 10 lines of code. Right? You can see it's not very difficult at all. So I'm going to put in 1,000 mesh points. Okay, in phi. Now my phi in this code is written as w. Okay, so I make 1,000 mesh points. I'm going to run from 0 to n minus 1 times a d phi of 0.03. Okay, I'm going to set my epsilon value to be quite large, just so you can see what's going to happen. And then sigma here is not important. Sigma is just 1/2. That's just the angle of the ship divided by pi. Okay, so the way that you do it is let me. In fact, it's a bit easier for me to just explain on the board here. You first lay down a series of points, okay, along phi. And so what you want to know is the value of q and theta at each of these mesh points. So we've laid down 1,000 set of points here. Okay, this first equation allows you to evaluate q given the value of theta. So you're going to guess a value of theta to begin with. For example, you can just set theta equal to 0. Use this equation to give you q. Okay, then let's say that you have n mesh points. N is 1,000. So you have a system. You need a system of 2n equations. You're going to get n of those equations that will tell you how q is related to theta from here. Once you know that, you're able to substitute this into the differential equation. This will also give you a set of n equations, or n minus 1 equations, and then one remaining equation imposed by the boundary condition. This produces a big matrix to solve, or a big system of nonlinear equations to solve, and then you just use Newton's method. So you have to discretize the derivatives here, write them in terms of finite differences, and then put everything into Newton's method. So that's essentially what this code does. Okay, let me go back to the code. So you can see I'm doing fsolve. Fsolve is the MATLAB canned solver for Newton's method. You're trying to solve a function which I've defined up here. You're trying to solve it for a set of unknowns u here, which corresponds to the theta values. Okay, so let's look at the function. The function is defined down here. Given the theta values, which is written as u, we first try to compute the integral. So the integral is computed here. Tau is log q. So you can see log q is equal to 1/2 log of phi over phi plus 1. And then you have to add that to 1 over pi. And then this is just the trapezoid rule applied to that integral. Okay? And then you define the derivative of tau, which gives you the derivative of q and then you form Bernoulli's equation here. And you can see some elements of Bernoulli's equation. It's written in slightly different notation, but this is to be read something like epsilon q squared q prime plus sine of theta is equal to 0. Okay? And then you go and replace the last mesh point with the fact that you need theta at 0 to be 0. Okay? I wrote that you needed q at 0 to be 0, which is turns out to be true, but because your system of equations is in theta, you're trying to solve for the theta values, and you get the q from the integral equation, I've put my boundary condition down here as theta. Okay? Obviously, this is something that requires some thought. It's not, you're not meant to understand everything right away, but you can see that how it's done and how it can be done quite compactly. Okay, so we're going to run this. It's going to run through Newton's method, trying to solve for these sets of q and theta values for this integral differential equation. It takes a little bit of time on my laptop. This is a very bit of a slow laptop. And then I'm going to try to plot it. Okay. Now, before I show you what the plot looks like, let's just do a little bit of analysis on this set of equations. If epsilon is equal to 0, right, this goes away. Right? I have sine of theta is equal to 0, so therefore theta is equal to 0. That's what I expect, because if epsilon is 0, if the speed of the stream is very slow, then my free surface should be largely flat. If theta is 0, this integral disappears, and I'm left with q is equal to phi over phi plus 1 to the 1/2. So what this is telling you is that if the speed, here's your epsilon equal to 0 problem. The flow is going past the rear of the ship. The angle here, theta 0 is 0, and the speed is this relationship that depends on the potential. It's not so important what it is, but you can see when phi is 0, the speed at this point is 0, and then the speed just simply increases to 1. As phi goes to infinity, this increases to 1. So the speed starts from 0 here, and then it speeds up towards the rear edge, approaching the free stream speed. Okay, and then the angle theta is always equal to 0. So let's have a look at what our numerical solution looks like. It's just finished. It usually just takes a second or two, a couple seconds on a faster computer, but on this slower computer, you can see. So now this is a graph of phi, the potential. 0 is the stagnation point. 30 is going downstream. And you can see Q starts off at 0 at separation, and then it increases towards 1. You can also see the waves that are forming here, right? So these are your free surface waves, which are being produced by the ship. And then finally, you can see the underlying curve, the dash curve, is the leading order approximation. That's the epsilon equal to 0 approximation. And you see the obvious issue, which is that it has no waves in this approximation. Okay? I can rerun this simulation with a smaller value of epsilon, and if I were to do that, I would see these oscillations are shrinking. I can also do an experiment. I can measure the amplitude of the oscillations, and I can verify that they are indeed exponentially small. So I'm going to need my exponential asymptotics to predict this kind of solution. Okay? So this is the waveless, the dash line is the waveless approximation. And we know, or we're expecting, that actually this approximation, if I don't have any waves in Q0, I'm not going to be getting them in Q1, Q2, Q3. It's going to be waveless to all orders. And so in fact, in this low Froude or low speed limit, the waves are exponentially small in this Froude number. So that the challenge is for us to compute that. Okay? So let me now show you how this is computed. So basically, the idea is always the same as for all the other problems. We know that if we can predict the divergence in this problem, then you basically know what the formula is going to be. It's always going to be just be 2 pi I over epsilon to the gamma e to the minus chi over epsilon. This component, what you need are those components that characterize the divergence, right? So in this problem, the asymptotic approximation in powers of epsilon is going to diverge, how do we approximate the divergence when it looks a lot more complicated in this case? Okay, so now the first thing we're going to need, so let's just write down our set of equations again. So we have epsilon q squared plus q prime plus sine of theta is equal to 0. And then we have a bit of a funny one here, log of q, that we're not exactly sure how to handle. This one's a bit more complicated. But it's basically log of phi over phi plus 1 to the 1/2 plus 1 over pi. And then this funny integral, this principal value integral, that makes the problem much more difficult. Okay? So in this problem, remember that phi, to begin with, phi, we're always thinking of phi as being a real number and positive, because that's characterized as the free surface, okay? The other thing just to remark is that this thing here, this integral, does make life quite difficult, because this is a global thing, right? It's not just a local. Whenever you have a normal differential equation, your quantities are somewhat local. Like, to predict the next value of the function, you just need to know the derivatives at the current value. This one is a bit of a beast because it requires you to know theta everywhere along the integral to get its values. That's why it's complicated. But we know that we can then try to expand. So let q be q0 plus epsilon q1 and so forth. And then you do the same thing with theta. And we know that by that procedure, right, at leading order, if I look at the order 1, I know that I'm going to get theta naught equal to 0 and q naught equal to phi over phi plus 1 to the 1/2. Right? And we know that that gave us a great approximation. I mean, it wasn't so great in the sense that it didn't give us the waves, but it still matched our numeric, what we were expecting for our numerics. The other thing that we know is that because of the singular perturbed nature of the problem, to get the next order in the approximation, right? So for example, if I want to get theta 1, I have to go to the order epsilon terms, and to get theta 1, I need q0 squared times q0 prime. So again, I have this trend where I have this singularity in the complex plane. This time it lies at -1. This singularity corresponds to the manifestation of the ship's corner. That's what it represents. Of course, on the free surface, on phi greater than 0, it doesn't do anything. It's just a singularity somewhere out there. But you know that this process where you're having to successively differentiate the low-order terms in order to compute the high-order terms, you know that generically this will often lead to divergence. And so theta 1 is going to need to differentiate this q0, where you have this branch point of a 1/2 power. And then q1 is going to depend on theta 1, and then theta 2, and theta 3, and so forth. And you're going to continue this cycle where you're going to always enhance the singularity at -1. And in general, it's going to lead to factorial over power divergence. Right? So that's basically what our plan is. Our plan is to try to predict this trend of divergence. And I'm going to show you how to do it for only the key component, which is the chi. Now, before we do that, there's an important step where we're interested in trying to analyze these equations in the complex phi plane. So remember, phi was originally greater than 0 in real, but we need an understanding of phi being complex, because that's where the singularities are. And so we need to complexify these sets of equations, right? Look at them in the complex plane. The first equation is very easy to complexify. Okay, so the point is that q and theta begin life in real phi greater than 0. But I can just think of this as a complex derivative in the complex plane. And this, just as you use differential equations to move along in real space, you can think of this as being a complex differential equation that's going to allow you to move in phi complex space. This integral is a bit more difficult to think about how to complexify it. But briefly stated, if I take this equation here, and I instead write down log q minus I theta, I think it is a minus I theta, it's a plus I theta, sorry, is equal to log q log of phi over phi plus 1 to the 1/2 plus 1 over pi. So I'm just going to write down what looks to be roughly the same set of equations. Okay, and I'm going to claim for you that this phi, here's my real phi axis, here's my imaginary phi axis, okay, and this phi is somewhere up here. I'm going to evaluate this equation when phi is in the upper half plane, right? So this is the physical free surface here, that's the physical water. And if I take this phi down to the axis, what do I get? Well, this integral originally runs from 0 to infinity. If phi comes down to the axis, I need to make sure that I split it up appropriately. This split will give me a principal value component. That led me to the dashed component of the integral before, and a residue contribution. And this residue will cancel with this residue on the left-hand side, hence returning me to the original set of equations. In other words, this equation here, when phi is complex, is the appropriate continuation of this equation off the axis. Okay? It's quite it's a big mouthful to explain really quickly, but as long as you understand that there's a recipe that allows us to take this equation when phi is real and then move it off into the complex plane and obtain another set of equations which is valid for phi being complex. Okay? So you can then essentially replace this set of equations and just add I theta here, and then this is no longer a principal value integral because phi no longer lies on the axis, it lies somewhere in the complex plane. So at the end of the day, you now have two sets of equations, and what you've done is you've opened it up. Q and theta originally were real valued on the axis, and this gives you a recipe for their values in the complex plane. We never had to think about this carefully, right? When we did our, when we were studying all sorts of problems, I don't know, Airy's equation, or, okay, we were doing Airy's equation, we just thought of x as being complex. We just thought, okay, this is a real valued differential equation, I'm just going to let x be complex. We never had to think about it that hard. To some extent, we're not thinking about it that hard either, except for this fact that there is an integral in this case, and then there's an adjustment that you have to do to think of things in the complex plane. Okay? All right, so now you try to write down the order epsilon to the n set of equations for this system. So you can go put in q naught and theta naught and theta 1 and q1, and obviously it's very complicated because it has this little beast that you don't really know what to do with. And it's also got logs, so you have to figure out how do I expand logs of an expansion, okay, and then how do I expand all of these terms. And so because of the nonlinearity in this problem, writing down the order epsilon, the n terms, is very complicated, right? But we sort of know what the trick is to predicting the late orders behavior from doing all the other problems before. We know that whenever you have a derivative, this tends to increase the divergence, because if you have a factorial over power and you take a derivative of that, the n comes up to the numerator and it increases that factorial. So if I write down the order epsilon to the n terms from the left-hand side here, I'm going to have a term like q naught squared qn minus 1 prime, right? This is going to be the order epsilon to the n from this one here. And then I'm going to have a bunch of stuff, right? Stuff like 2, q naught, q1, qn minus 1 prime, all the other nonlinearities of this. Sorry, this is n minus 2 prime. And then I'm going to have the expansion of the sign, and with the sign I have to put in theta naught and etc. but I'm going to have basically theta n times cosine of theta naught here, plus dot dot dot. Okay, obviously it's very complicated. You can look at the notes where I list a few more terms from the expansion for you to see. But the key is for you to notice that this qn minus 1 is lagged, the index is lagged by 1, but then because of the derivative, it will be equivalent in order to theta n here when you try to do the balance. And all the other terms will not be so important to determining this crucial chi. Okay? Okay, so then the next thing is you're going to put the same q naught, q1, and theta naught into the lower set of equations. Okay? And so you have to expand the log q term here. And the log q term will get you something like qn over q naught. Right? So for example, you'd have to do something like log of q naught, and that becomes a 1 plus epsilon q1 over q naught plus da da da. And then that becomes log of q plus log of this factor, and then you have to expand this for small epsilons, etc. But at the end of the day, the relevant term will be the qn over q naught. You can kind of see there's going to be a q1 over q naught. There's going to be a qn over q naught plus dot 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 plus I theta n. That one's very simple, at order epsilon to the n. This term is not involved because this is log q naught, right? So that's not involved at order epsilon to the n in general. And then you have this thing here, okay? But we're going to assume, so I'm going to write it down. Okay, so this integral here, which is very confusing to think about right now. But I'm going to just tell you that this integral is not important in the limit that n goes to infinity. The way to think about that is that, one way to think about it is that if I take the limit as n goes to infinity, but I also take the direction in which I tend towards the singularities in the complex plane, these ones will blow up, right? These guys will blow up because these guys are factorial over power. This one will not blow up because you're essentially just evaluating theta n along the axis and then integrating it. You're taking phi to a point in the complex plane, but this thing remains, in a sense, well behaved. So there's an argument that you can apply that essentially says that this integral in the limit that n tends to infinity is not an important component. Okay? But you end up with the residue from that integral, by the way, which produces I theta n. Okay, that was, the argument of that integral being subdominant is really, that's the tricky business. Once you have kind of illustrated the main dominant terms as n goes to infinity, this allows you to basically tell you that theta n is then, what is it? It's minus I times qn over q naught plus dot dot dot. And you put that one into there, okay? And then what will that tell you? Well, it'll tell you that q naught squared times qn minus 1 prime is twiddles I times qn over q naught, because cosine of theta naught is just 1 because theta naught is 0. Okay, there's other terms, of course, there's other terms like qn minus 1, etc., that I'm not writing down. You can refer again to the notes for the full gory details. Okay, so now you've reduced it down to this thing here, and then you're just going to try your usual ansatz. So your usual ansatz is this. It's a factorial over a power. And then you put this, you take a derivative of this one here, you put it into there, and you'll notice that the balance is going to give you minus chi prime on the left-hand side, q naught squared is I over q naught. And so that tells you that chi prime is like minus I over q naught cubed. Okay? remember that Q naught is this thing which represented the ship. So the geometry of the ship is going into this crucial singulant. Remember as well that the chi should be 0 at the singularities that you're interested in, that's producing the divergence. And so this will tell you that to get chi, you just simply need to integrate phi plus 1 over phi to the 3/2. Okay, this is a dummy variable, and you integrate it from the singularity. Okay, so we've really done this quite quickly, but hopefully just to illustrate to you the idea, which is you have this complicated problem. If you can somehow predict the way that the series is diverging and produce this kind of factorial over power expression, then you know that the exponentials are in a sense universal. They're 2 pi I over epsilon to the gamma, this q e to the minus chi over epsilon, plus a complex conjugate in order to be real along the axis. So you can almost jump right away and see if you can predict the magnitude of these oscillations. Okay? The other thing that you know is that the Stokes lines are given by some criteria that's given by this chi. The Stokes lines are given by where the real part of chi is positive and the imaginary part of chi is 0. So you just need to plot this. You need to somehow integrate this numerically or analytically, or otherwise you can actually do this analytically, in fact. And then you just need to plot the curves where this occurs, and that should tell you where the waves are switched on in the problem. Okay? Let me show you, let me write out the main result again, and then let me show you the Stokes lines for this problem and the main conclusion. So, of course, if you're doing this in practice, well, you're going to take a long time to do it because you have to do all these expansions, but you'd get the Q and you get the gamma by the same procedures, but it's very similar in spirit to the simpler problems I showed you. The main difficulty is that it's a harder set of equations, but the idea is the same. Okay, so I was doing this, and I think my chi that I wrote down is actually off by a sign, so I'm going to correct it here. I'm not sure where that sign comes from. I want to move on quickly. But I think that in this case, the problem is that the integral of chi will be I and then 1 over q naught cubed d phi. Okay, there's a dummy variable from -1. And you can verify that this is something like 3 pi over 2. 3 pi over 2 plus I times w minus 2 over square root of w over w plus phi over phi plus 1. My w's are phi's. Plus 3 times arctan. 3 times tan inverse of the square root of phi for phi plus 1, and I might be off screen at this stage here. Yeah, I just managed to write it down. Okay, so there's our phi expression. And what does it look like if you plot the real part of chi positive and the imaginary part of chi equal to 0? Well, this is the complex phi plane. Remember that your physical free surface, real life, is along this edge here. This edge here, phi greater than 0. There's a singularity at -1 in this problem, and in fact the Stokes line looks like that. So along this, this is that criteria. There's essentially a Stokes line in the upper half plane, because to perform this procedure you had to first analytically continue into the upper half plane, and there's a Stokes line from the lower half plane which basically goes in the other direction there. So in this problem, the idea is that you begin life here near the stagnation point, Q is Q naught plus epsilon Q1 plus so forth, your basic asymptotic expansion. And then as you cross the Stokes line, you have the usual asymptotic expansion plus an exponentially small term, e to the minus chi over epsilon. And the form of that exponentially small term is given by this universality, by this chi. Okay? So you can see almost directly from this expression that when phi is a real number, this is the real part of chi. So that tells you that on this surface, the waves will be e to the minus 3 pi over 2 epsilon times an oscillation. The cosine of the imaginary part of chi over epsilon plus dot dot dot, plus a phase shift, plus other components that you have to figure out. But that should give you a measuring stick of whether you're right or wrong. You should be able to measure the waves and check, is it really minus 3 pi over 2 epsilon? Okay. What I've done here is I've taken the previous code. I'll take this code here. And I've just plotted chi. So I'm going to take the, let me uncomment this firstly. How do I uncomment in Windows? Like that, maybe? Okay, here we are. I'll run this first and then I'll explain to you. So in addition to the previous solver, which is going to solve for the waves at epsilon equal to 1, pretty big number for epsilon, I'm going to plot 2 times e to the minus chi over epsilon plus its complex conjugate. Or rather, e to the minus chi over epsilon plus its complex conjugate, so you get 2 times the real part. Okay, let me go back to the picture here before you. So I put in my chi here. I've not put in any other components, right? So there's kind of an amplitude here that I've not put in because I'm just going to assume that this is going to give me roughly the shape that I want. And then I'm going to plot the base solution, Q naught, and then just add that exponential there. And then look at that, right? Somehow I'm off by a phase shift. I'm probably just a negative sign off. But you can see that you're predicting the waves pretty well, right? All we're doing is just plotting a cosine or a sine with the e to the minus 3 pi over 2 epsilon factor in there. But it looks pretty good, okay? So how would you check this? What you would have to do is you go to your numerics, you run this at different values of epsilon, and you just measure the waves at different values of epsilon, and then you plot them, and then you try to compare with your asymptotic prediction. But you'll see that actually it gives you a bang-on prediction. Of course, you can go and get all the other components of the exponential, but this is the key idea. Okay? So I've done this really quickly, but you can just see how magical this theory is. Let me finish in the last couple minutes with just telling you the bigger picture of what we've done. So how do we vary this kind of problem? What other things can we do now that we understand this underlying theory? Well, of course, there's nothing stopping us from designing a different kind of ship, right? So let's study a problem where the flow is going past the ship, where I have different angles, right, which characterize the body of the ship, and there are different points, there are different singularities along the body of the ship. And if you were to do that, there's nothing that's hard about that problem, you would find that the leading order solution, as you can imagine, will be some kind of expression in phi, and then this will be something like phi plus the first singularity to the one to a number, phi plus the second singularity to another number, etc. And there has to be some kind of condition that says all the angles have to add up to be pi by 2. And what are you going to see in this picture? Well, what you'll see is that there's essentially a Stokes line that comes from every point, or potentially every point in the geometry. And across each of these points, you're going to switch on an exponential. And the form of that exponential will be the same. It will be e to the minus chi over epsilon. They're just integrated from different points in the complex plane. Now in practice, if you're doing this with a computer, you might only see the biggest one because all of these exponentials will be exponentially, one exponential will exponentially dominate the other exponential. So in your numerics, you might only see the biggest exponential. But you can have this kind of theory. You can then ask yourself, is it possible for me to design a ship so that I get total wave cancellation? Can I make it so that the contribution from one singularity of the ship will cancel with the contribution from another singularity ship? You might kind of argue that, well, actually, because the magnitude of the exponentials that are switched on scales with the distance of the singularity from the main surface, that actually you can reduce the waves by making some kind of obstruction which is deeper and deeper down the flow, because essentially there will be a Stokes line from this one, maybe a Stokes line from this one, but the magnitude of the wave that's switched on, because this is so far down from the free surface, might be smaller. Obviously, this is an unrealistic flow because in this kind of regime, you shouldn't really be doing potential theory because actually you'll have all sorts of wave separation and flow separation, that kind of stuff. But the theory will still give you, nevertheless, the magnitude of those waves which are switched on. How do you do the problem now for a step? Okay, so we were looking at surface piercing obstructions. Well, for the situation of a step, the potential plane looks a little bit different. The potential plane, instead of being a semi-infinite region that you're interested in, the potential plane is now located within a strip, and the flow is contained within the strip because this is at one value of the stream function, this is at another value of the stream function. But then what you can do is you can map this strip to an upper half plane. This is what I mentioned before, where the free surface has been mapped to this axis, the solid boundary has been mapped to this section of the axis, and your flow is in the upper half plane. And then now you're in familiar territory. If you can just write down Cauchy's theorem for this problem, you'll see that actually the two problems that we studied, the ship wave problem and the step problem, are very similar, just up to an additional coordinate mapping. But in this problem, you will obtain a very similar theory, that from each singularity, there are these Stokes lines. They're dictated by this chi, this singulant, and if you can just derive the chi, you'll be able to predict the waves which are formed downstream from this object. Okay? We're at 4 o'clock, but one last variation for you. What if I put time dependence into this problem, right? We've predicted a theory where the waves are exponentially small and associated with singularities in the complex plane. Is it the case that if you put time dependence in the problem, will that fundamentally change this picture? And I think the answer is largely no, that if the waves are exponentially small in the steady state version, there's an analog of these exponential asymptotics for the PDEs as well, but then that becomes kind of current research. That's much harder because the setting is very different, but we believe that in theory the same ideas hold. And then finally, the last thing I'll say is that here we looked at gravity waves, right? So if I have an obstruction and I have water flow that goes past this obstruction, then gravity waves will be formed downstream from the object. But actually, your free surface equations should also involve a small amount of surface tension, right? Water includes surface tension, and the effect of surface tension is to produce small-scale ripples, little capillarity ripples, or capillarity waves in your free surface, and those can be shown to also be exponentially small when the speed of the stream is small. And what you find when you do your exponential asymptotics for this problem is that some of these Stokes lines are gravity associated, and they predict a gravity wave, e to the minus chi, let's say call it chi g over epsilon. And actually, there are Stokes lines which are capillarity motivated or dictated by the force of surface tension. And you can predict capillary waves as well. And again, you have this very beautiful theory where it boils down to trying to decode the asymptotic divergence. This is the idea that any problem where you have the factorial over power divergence of your asymptotic expansion, it must be accompanied by these exponentially small terms. Now, it is not always the case that the Stokes lines will hit the physical free surface. So in a lot of problems that you might also be studying, you might have asymptotic divergence, but because the Stokes line doesn't hit the free surface or doesn't hit the physical reality, you don't see the manifestation of these waves. But then these are also problems which are fascinating because of this property. Okay,